Hi everyone, and welcome to the first video on convolutional neural networks. So in this video, we introduce the basic operation behind the founding component of convolutional neural networks, which is basically the convolutional kernel. Right, so what is referred to as convolutional neural networks are really architectures that have convolutional layers. And so a convolutional layer, unlike a fully connected layer, this layer has sparse interactions. So every output unit depends only on few input units. And this sparse interaction is defined by a convolutional kernel that is basically shifted throughout the input to give me the output. Right, so convolutional neural networks were initially developed in 1989 for handwritten digit recognition, and they are basically inspired by the mathematical convolution operation, right? But they apply a slightly different operation, which is called mathematical correlation, and we'll get to it at the end of this video. So what is mathematical convolution? Basically, when I convolve two signals, let's say I have two continuous time signals, x of t and w of t. So think of x as the input, right, and w as the kernel. Then this is basically the s of t. The output is the integral with respect to, so I replace the time parameter t by a variable a. Right, so I integrate with respect to a from minus infinity to infinity, x of a times w of t minus a. So graphically, if we were to do this, how will it look like? So let's say x is something like this, right? So this is x. This is x of a, right? And this is a is the x-axis, right? So the time variable becomes, we call it a. Okay, now let's say w, which is the kernel, looks like this, right? So this is w of t, right? Or w of a. So this is w of a, and a is the x-axis, right? So we have here w of t minus a, right? So t is a constant because we are integrating with respect to a. So first you have w of minus a, right? So this is w of minus a. And then you shift it by t. So for every t value, so let's say I want to know the value of the convolutional at t equal 1. What I do is that this w of t minus a, we shift it by 1, right? So this is w of 1 minus a. And then we do a dot product, right? So here it's continuous time, so we multiply every point in w of 1 minus a by the corresponding point in x of a, and then we integrate, right? So it's as if first I flip w, and then we shift by t, and then we have a dot product, right? Now in mathematical correlation, and we'll get to it, the only difference is that there is this flipping doesn't happen, right? So instead of w of t minus a here, we have w of t plus a. Okay, but let's first discuss the convolution. So I have the w, I flip it, and then we shift it. So why do we do it in this way? So this is a very commonly used operation in signal processing in general, right? And one of the reasons of designing convolution in this way, and one of the reasons that it is useful, is that it has a property called commutativity. And the commutative property means that x of t convolved with w of t is the same as w of t convolved with x of t. And the reason is very simple. So w of t convolved with x of t is basically the integral of w of a times x of t minus a dA. If we make a change of variables and call t minus a tau, then from what we know in calculus, d tau is the same as dA, right? The intuition behind this is very simple. What the d tau means is that a small change in tau, right? And whether tau equal a or tau equal minus a, a small change in tau corresponds to a small change in a, right? So d tau equals dA. So think of this, the d thing is caring only about the step size, not the sign of the variable. So if we do that change of variables, because d tau equal dA, then wt convolved with x of t would be equal to basically integral x of tau w of t minus tau d tau. And this is the same, and because a goes from minus infinity to infinity, tau will go from minus infinity to infinity. This is the same as the original, so x of t convolved with w of t, right, is the same as w of t convolved with x of t. So this is in continuous time. Now in discrete time, it's basically instead of integral, you have a summation, right? So it becomes a sum of x of a w of t minus a, right? So if x of a in discrete time is something like this, right? So this is discrete. So these are steps, right? So let's say this is x. Let's say w looks like this, right? Then I basically have x of a, this is w of a, then w of minus a is the mirrored version, right? So it's here. This is w of minus a, and w of t minus a, let's say t equal 1, right? Let's say t equal 2, so w of 2 minus a, so this is w of minus a, this is w of a, this is x of a. W of 2 minus a is basically this, and this. And I multiply by x of a, element by element, and then I sum. Now let's say we don't have only one dimension, we have 2 dimensions. Then basically the kernel, instead of being a signal in 1 dimension like this, the kernel will be in 2D. So you can think of it as a square, right? And typically, the kernel has a finite number of non-zero values, right? And is centered at the origin, right? So for example, a 3 by 3 kernel, you can have it by a grid like this, right? It's typically centered at the origin and has the same number of dimensions in has the same size in each dimension, right? So has the same number of non-zero values in each dimension, right? So this is, for example, a 2D kernel that is 3 by 3. For 10, let's make this 10 as well, because we said non-zero values, right? So in 2 dimensions, it's basically the same operation, but in 2 dimensions. So x of ij convolved with wij is the sum over the 2 dimension, x of mn, w of I minus m, j minus n. If I do a change in variables, this is the same thing as saying x of I minus m, j minus n times w of mn. Sounds good? Now what happens in neural networks is basically mathematical correlation and not mathematical convolution, right? But it's called convolution, probably a historical reason. So mathematical correlation is slightly different. If I take this equation right here, right? This is x of I minus m, j minus n. In the implementation of mathematical correlation, that is in convolutional layers, in machine learning libraries, it's x of I plus m, j plus n. Not x of I minus m, j minus n, right? So it's as if I took the original kernel and I flipped the kernel. So wmn, I replaced it by w minus m and minus n. And the intuition is that it really doesn't matter, because that kernel is something that we learn, right? So the parameters of the kernel, these are the weights of the convolutional layer, right? So we actually learn the kernel. So whether you do mathematical convolution or mathematical correlation, right, it shouldn't matter, because you can flip the kernel. You can learn the flipped kernel instead of the original kernel, right? So if there is a certain optimal solution, right, with a certain kernel, you can learn the flipped values of them when you apply mathematical cross correlation, right? So basically it's a very simple operation. So what's a convolutional layer? You have, let's say, in one dimension, I have my kernel, I pass my kernel, right? So if I apply this operation here, right, with if I consider this transformation, so I pass the same kernel across all the input units. So for example, I want to know the output of so I have multiple units, the input to the layer, multiple units output to the layer, right? So let's say I want to apply, and my kernel is 3 values, 1, -2, 4, right? So what happens is that when I have the output unit here, I multiply this unit by 1, this unit by -2, I multiply this unit by -2, this unit by 1, and this unit by 4, right? If I want the output unit here, I multiply this unit by -2, this unit by 4, this unit by 1, right? So it's as if, so I have the same weights and I slide this kernel through the input. Sounds good? So that's, if I have 2 dimensions, then I'm sliding a kernel that looks like the square here, right, across the 2 dimensions. So if I want an output at ij, then I center the kernel at input ij, and then I multiply by the weights of the kernel. Sounds good? So these weights are fixed across all the input values, right? Across all, the output units. So the output units are sharing weights, meaning the weights connected to the output, to this output unit, right, are the same as the weights connected to the next output units, are the same as the weights connected to the next output unit, and so on. Okay? So the last thing that I want to say is that basically one way to think of convolution as a multiplication by a matrix, and this matrix is very sparse. This matrix is called Toeplitz matrix if you have 1D convolution, and the Toeplitz matrix basically looks like this, right? So this is a kernel of size 2 in 1 dimension, then basically this is the Toeplitz matrix. So the second property in convolution that we can notice here is sparsity, right? A fully connected layer corresponds to multiplying by a full matrix. Here we multiply by a sparse matrix. And the first property that we noticed is basically the parameter sharing. Now there is a third property called equivariance to translation. And that property basically means that if I shift the input values, the output gets shifted by the same value. In the next video, we will focus on these 3 properties as a motivation for convolutional neural network. Thank you.